My name is Payal and I am a research scholar of this esteemed department. I feel very grateful and equally excited to be the host of this session. I request Professor K.K. Ghosh sir, chairperson of this session, to occupy the seat on the dais. Uh, I now request Professor Agrawal ma'am to welcome Professor K.K. Ghosh sir with a floral bouquet. I would like to introduce our chairperson for today's session. He is the professor and head of Department of Chemistry and director, Center for Basic Sciences, Pandit Ravi Shankar Shukla University, Nagpur, and sorry, I'm so sorry, Raipur. And he has published 200 research papers under him. Uh, may I please request Professor K.K. Ghosh sir to chair the session for today? Thank you, sir.
Thank you. Good afternoon. A distinguished scientist, Honorable Professor Dikshit, Professor Soni, Professor Avasthi, Professor Aswar, my young friend Venkatesu, Professor Dhonge and delegates. I feel proud and honored to be part of this 108 Indian Science Congress. In this session, I think there is 2 lectures invited. First is, I think, Professor Dikshit, and second is Professor Avasthi, I think, perhaps. Professor Venkatesu. So, it is customary that we should talk something about the very renowned speaker. Professor Arvind Dikshit needs no formal introduction because he was a vice chancellor of a very prestigious university, that is B.R. Ambedkar University, Agra. And basically, he is a material scientist. So, with this short introduction, I request Professor Arvind Dikshit sir. He is an academician as well as an administrator. So, it is my pleasure to invite Professor Dikshit for this session. Thank you. And time limit is, I think, 15 minutes. Yeah. Thank you, sir.
Thank you, Professor Ghosh. As already said Professor Ghosh, I am ex-Vice Chancellor. Being Vice Chancellor is a jack of all trades, master of none. Because in administration, you have to do simply work like a daroga. And you have provide facilities for the academicians, scholars to work in healthy atmosphere. Now, I come to my topic, development of polyphosphazine for high-end applications. The content of my presentation, introduction of the polyphosphazine, organic polymers, advantage of blend prepared by the polyphosphazine and organic polymers, synthesis of base material, that is polyphosphazine, preparation and characterization of polyphosphazine fiber for flame retardant applications, preparation and characterization of ultra-high molecular weight for polyethylene fiber by melt spin technique, preparation and characterization of flame retardant polyacrylonitrile fiber, and conclusion. This is the combustion of the cycle of polymer. Polymer on pyrolysis produces flammable product, combustible gases, tar, liquid, and other part is non-flammable product, non-combustible gases, solid residue and SB. Flame retardant fillers. We have taken three type of the flame retardant. One, organic halogen containing fire retardant. The property is conventional, economical, and don't affect much to physical properties such as strength. The demerits of the organic halogen containing fire retardant is the toxic species like dioxins, furans generated during the combustion causes serious environmental contamination. Inorganic halogen free, low smoke, non-toxic, environmental friendly. Demerits, it required high level of the loading, that is the cost effective, leading to additional cost producing different decrease in the physical properties of the polymers. And third one is the phosphorus nitrogen based fire flame retardants, halogen free, low smoke, non-toxic in nature, low loading and cost, good flow and the processability, work well with the synergies like melamine or other flame retardants. Demerit, it needs 30% of the loading. 30% loading is also cost effective. The polyphosphagene are a class of the noble inorganic polymers having the molecular structure. The properties of the polyphosphagene depends upon the nature of the side group. That is the R1, R dash. Properties depends upon this. The different side groups generate different properties from elastomers to thermostat. It is hydrophobic in nature also, polyphosphagene containing compounds, that is hydrophobic and hydrophilic in nature. Amorphous to crystalline. Different type of the properties are shown by the same molecule. The inherent properties of the polyphosphagene includes high oxygen index, low smoke emission, no corrosiveness, low toxicity of the combustion gases, environmental friendly. Excellent, ये जो nature है, excellent, works as a compatibilizer for the polymer blends. Drawback of the polyphosphagene. Fluoroalkoxy and orthoallyl phenoxy substituted polyphosphagenes are elastomeric in nature, so there is a dimensional instability, hence tough to make self-standing flame retardant fibers. Many organic polymers like polyphene, polyolefin have high susceptibility to the flame and have low thermal stability, which limits their application in the various fields like the electronics and electricals, structural applications, transport or building. Many flame retardant additives like halogenated inorganic salts, nanosilicates are used to overcome this drawback, which succeeded to get the flame retardancy. But effective is the lowering their mechanical property and processability and easily get bloomed or leached out during its processing. As I have said earlier, the beauty of the polyphosphagene polymer is crystalline versus amorphous, hydrophobic, hydrophilic, same compound show the different properties. Advantages of the blend. Polyphenes provide dimensional stability of the polyphosphagene. Polyphosphagene uses a flame retardant additive to make polyolefin flame retardant without losing their inherent properties. Synthesis of the polyphosphate. Simply we have take the ammonium chloride, phosphorus pentachloride in chlorobenzene. There is a continuous flow of the nitrogen gas. Nitrogen gas contains water content and some oxygen. By using washing chamber like pyrogallol, use of the pyrogallol, the problem of the oxygen is eliminated, and concentrated sulfuric acid, the moisturizer. Then after using washing chamber for the nitrogen gas, we produce oily mixture of the linear and cyclic polyphosphate. This is 60 to 70% cyclic polyphosphagene and 30 to 40% linear polyphosphagene. This is the oily or wax-like residue, and this is the trimer. Yield is 57% trimer, approximate tetramer 28%, higher cyclic chlorophosphagenes, penta to decamer. Here, hexachloro triphosphagene. This is a cyclic in nature. Ring is opened by using calcium sulfate in sealed tube. The temperature 250 to 260 degrees centigrade and 18 to 20 hours for the reaction time. Now, ring is opened. Here we are seeing this is the one chloride and second. These halogen, they are replaced by B, C, D, E, F and G. If we take sodium metal, ethoxy ethanol, that is B. This compound is formed. All these are reactions carried out in the vacuum sealed trimer. This is the vacuum sealed trimer converted into polyphosphagene. Ring is opened and after we get product. The FTIR graph, the polyphosphagene is shown. We have got a patent. This is a group research in combined with the DMSRD Kanpur. Now, thermal analysis of the synthesized polyphosphagene. This is the original dichlorophosphagen. This is the. After blending with polyethylene, MIP, butanol, allyl, this shows the TGA graph shows the remarkable change in the properties. The polymer fibers, organic polymers, as all of you know, flexible molecules and stiff molecules. By the melt spinning, wet spinning, dry spinning, and stiff molecule melt and wet spinning, nylon, HMPWD, ultra high molecular weight polyethylene, these are the formed. Fibers. Dry spinning from the solution, polymer solution, spinneret, take the wheel, cellulose acetate. Here melt spinning, take away the nylon 6. Fiber, spinning melt. Polymer chips, heating, grind, pool pump, filter, spray, dry diffuser, moisture conditioner, finally yard driver to bobbin drive. The fiber spinning is used to manufacture thin synthetic fibers. A filament is continuously extruded through the orifice. In the diameters, they contain 100 mm and smaller. The molten polymer is first extruded through filter screen pack to eliminate small contaminants. It is then extruded through a spinner, a die composed of a multiple layer, 1 to 10,000 holes. The fiber are drawn to their final diameter, solidified in a water bath or by the force, convection and wound. Spinning of the polyphosphagene fibers, constants. Being elastomeric in nature, dimensional are unstable, hence very tough to make self-standing fiber. By the blending of polyphosphagene and the ultra-high molecular weight polyethylene, blend PPZ to the quantity of PPZ approximately 8% and polyethylene is the 92%. Symmetric representation blend perfection. By the addition of polyphosphagene, we are seeing the remarkable change. The mechanical and thermal properties of the polyphosphagene and ultra-high molecular weight polyethylene. The tensile modulus, PPZ pure 0, but blend 0.47. Tensile strength 0, 18. The elongation at the break 285. MFI no flow 2.8. Onset 300, 325, 500. LOI 56 and PP jet blend 48. As you know, above 20 LOI, flame retardancy increases. Spinning of the search time 5 minutes. Yeah. Spinning of the UHMV fiber by the melt spinning. The only solution are gel spinning. Melt spinning is not possible. Mechanical and thermal properties of the OMHP and the PPZ blends. This is the 4.3 tensile modes. After blend, 3.7. Tensile strength 230 to 196. Elongation 64 to, this is the curve. No flow 3.8. Onset 453. 500 constant. LOI. This is the 19.5, less than 20. It increases to 29. ULI test, catch fire, 0. The spinning of the flame retardant polypropylene fiber. Poly 8.1, that is 0.78. Here we have the increase the percentage of polyphosphagene from 8 to 10. Tensile strength 30, 20. Elongation 100, 160. Onset 225, 250. 370, 400. LOI, this is the 18. Increases to 28. Glass transition minus 20, minus 35. It also qualifies the cone calorimetry test results. Preparation of polyacrylonitrile PAN, PPZ blends. On the same manner, polyphosphagene, polyacrylonitrile, twin screw extruder, This is the conditions. Fire retardant epoxy reagent for the Pinaka multi-barrel ranches. इसका practical use, this is the practical use of the blending. It is possible to incorporate different types of the properties as we need, we can add it. I am very thankful to Professor Saxena and the Indian Science Congress for providing the opportunity. Thank you.
Thank you, sir. Thank you.
Hello.
Okay.
Please join me. Big hand.
Thank you so much, sir. I now request Professor K.K. Ghosh, sir, chairperson of the session, to present a memento to the speaker of the session, Professor Arvind Kumar Dikshit, sir. Let's move on to the second lecture.
Now from polymer, now we are moving towards a very important area of physical chemistry, and not only physical chemistry, all the chemistry, the ionic liquids. And I should say the speaker is one of the brilliant physical chemists of our country. Basically, at present he is a professor of physical chemistry at University of Delhi. He did his MSc from ASB University, Tirupati. And most importantly, you all know about the Journal of Molecular Liquids. And he is the editor of this Journal of Molecular Liquids. And he has published large, basically he is a biophysical chemistry. And he has done a lot of work in the area of protein folding, ionic liquids. And I think he has published more than 235 papers at a young age. And many of his students are working in various parts of the globe. And he has got large number of awards, not only from the Science Congress, even from Indian Chemical Society, as well as the CRSI, Chemical Research Society of India, bronze medal. And he is also member of the editorial advisory board in, you all know, ACS Sustainable Chemistry, Engineering Impact, ACS Journal, member of the advisory board of Journal of Chemical Thermodynamics, and of course member of the editorial board of the Journal of Ionic Liquids. And I really feel proud and privileged to welcome my young friend Venkatesu and request him for he is a fantastic teacher. Thank you very much.
First of all, I would like to thanks to the chairperson, Professor K.K. Ghosh, for his nice introduction. And also, I want to express my sincere thanks to the Indian Science Congress Association and the department of this university. Particularly, I want to thankful to the Professor Sudhakar Dongade sir, because since yesterday he is taking care about me, because we know each other since 2008. So a special thanks to the Professor Sudhakar Dongade sir for his nice hospitality and nice his affection on me. Thank you, sir. Now coming to my talk. So I'm going to talk about ionic liquids as a green solvents for enhanced stability of properties against the multiple stress. So now back. Oh, it's moving. Yeah. So just now we are celebrating 100 years sanitary years to our University of Delhi. Now I'm going to talk about the protein folding stability in the presence of ionic liquids. So mainly my research focusing on protein stability in biomass, protein folding, unfolding studies in the presence of ionic liquid, as well as nanoparticles and bio-nano composites of polymer and nanoparticles. The last one, but not least, polymer phase transition. So in these areas, we are working at the moment in the Department of Chemistry, University of Delhi. So before talking about protein stability, first the protein stability. What is protein stability? The protein stability means the net stability of protein defined as the difference in the free energy between the native state and unfolded state. You may see this is native state. I'm comfortable in that down. Okay, so you may see this is net stability, this is the folded state, and this is unfolded state. So if you have folded state, one of these stresses, cellular stress or addition of solvents or changing the pH, the protein go to unfolded state. So if you have folded state and unfolded state, the difference of the free energy is giving the net stability of protein. So this is the protein stability basic definition. So how to predict the protein stability? So generally we are using the transition temperature using thermal fluorescence, thermal CD or differential scanning calorimeter. So once you put the sample in the instrument, then slowly increase the temperature. At a certain point, you can see here, the temperature is raised up to here, then suddenly it makes transition from here folded state to unfolded state. So this state we can say transition temperature. So from this point the protein starts denature. Okay, you can see here guanidine chloride. This is the basic denaturant for the biological denaturant for the protein. You may see at the low concentration protein is folded state. When increase the concentration, suddenly it is making transition from this state to this state, and this we are calling transition state. Okay, fine. Now this is one method we can determine. The another method is free energy changes. So free energy changes also we can predict using any calorimeter, isothermal titration calorimeter or differential scanning calorimeter. When you increase the concentration of solution, the free energy changes are increasing. So that means protein is in folded state. Whereas when increasing the concentration of some kind of solvents, the free energy changes are decreasing. So that means protein is in unfolded state. So using this basic concept, one can predict whether protein is in folded state or in unfolded state. Okay, so I already told you this is the folded state and this is unfolded state. So this point you can say intermediate state of the protein structure. So here you have 50% of folded state and 50% of unfolded state. So that's why this part we are considering intermediate structure of the protein structures. So fine. So this is about basic information about the protein stability and it is related things. So every organism, including us, everybody is facing different kinds of stresses. Okay. So for example, environmental effect and heat effect and pH changes, radiation, cold effect and concentration effect. So if different kinds of stresses on the inside the cell, what is going? So if you have different kinds of stress, the organism is going to denature because of these stresses. Now the point is how to control these stresses and how to keep into the normal state, folded state. So that is the challenge nowadays for biochemists. So, okay, so you can see here very clearly this is the protein structure. So up to here it is no problem. When you apply these kind of different kinds of stresses, what is happening? The protein is getting denatured because of these effects. So now our point is how to control this. For that, nature has given some kind of co-solvents. Okay, so if you add this co-solvent is giving protection and keeping into the folding form. Now the question is, which co-solvent is suitable to give this kind of protection? So if you see the chemical point of view, mainly we have organic liquids and ionic salts. Okay, so if you consider organic liquids, mainly they are contributing air pollution, ozone depletion, and health human related problems. So these organic liquids never support to the protein to against these stresses. Then if you consider ionic salts, most of the ionic salts, the melting point is more than 100 degrees. So at this condition, it is not giving any support, any protection against these kind of stresses. Then what is solution? We can't play with the organic solvents as well as ionic solvents. Then during last 2 to 3 decades, lot of research work has gone in this direction. Then finally, people found different kinds of sources, that is biomass, solar energy, utilization of solar energy, nanoscience, waste utilization. The last one, but not least, that is ionic liquids. It is a part of green chemistry. So what we did, we consider this ionic liquid initially, then how these ionic liquids are giving protection against these stresses, we can see one by one. So I'm not going to talk about details about these ionic liquids, already it is known things. But in 1990s, the history of ionic liquids started, but people not recognized the importance of the ionic liquids. Later on in 2000 around, people recognized the importance like a small tree. Later on, it is expanded different fields of the different scientific fields, including biotechnology, medicinal applications, analytical, thermodynamics, electrochemistry, organic reactions. Nowadays, people are also considering nanochemistry also. So like this, their application vastly increased in different scientific fields. So my consideration is only the biocompatibility of this ionic liquid and biostabilization towards the protein structure. Okay, so very recently we have reviewed the applications of this ionic liquid and we published as a sustainable chemistry and engineering. So here we covered most of the applications, including protein stability and also polymer phase transition also. Okay, so since we are working in different field in my research laboratory, so we have decided to review all the applications, most of the applications which we are working in my laboratory. Like that we consider, then we reviewed their applications. First in 2012 we published a chemical review. This is mainly related to the history about ionic liquids and towards protein stability. Later on we published different reviews related to protein folding, thermal stability, and also thermodynamic properties which are involving ionic liquids and polymer phase transition. Like that we reviewed in different journals. So now what we are working at the moment in our research laboratory, first we are working simple amino acids, cyclic dipeptides, then commercially available enzymes as well as proteins. So first what we did, we have taken simple glycine, diglycine, triglycine, tetraglycine, then we have taken different kinds of ionic liquids. So initially what we observed here, as I mentioned in my beginning slides, you can see here when we increase the ionic liquid concentration, the free energy transitions are increasing with increasing this concentration. That means these ionic liquids are giving protection towards the glycine structure. Then similarly we observed same conclusion for glycine, diglycine, triglycine and tetraglycine. Later on we have taken cyclic dipeptides, a little bigger than the glycines. So here also we observed when we increase the concentration of ionic liquids, the free energy changes are increasing. So that means the ionic liquids are giving protection towards these cyclic dipeptide structures. Then we have taken alpha chymotrypsin, which is enzyme. It is folded with 2 domains. It's consisting 245 amino acids. This enzyme people are using in cancer therapy also. Then we used CD analysis. So here you can see without ionic liquid, the transition temperature is 42 degrees Celsius. Whereas when we add the ionic liquid, the transition temperature rapidly increased up to 65 degrees Celsius. So that means up to 65 degrees Celsius, my ionic liquid is giving protection for the alpha chymotrypsin native structure. Then other ionic liquids are also following same trend, but all the transition temperatures are obviously higher than this buffer point, control point. Then we have worked other ionic liquids also as a function of concentration. Here also we observed the transition temperatures are increasing with increasing the ionic liquid concentrations. So here we did fluorescence analysis. You can see here at low concentrations, there is no change for the fluorescence intensity. So that means these aromatic residues of these proteins are stabilized. Whereas increasing the concentration, the wavelength is increasing towards redshift. When you have redshift, that means protein is getting destabilization, unfolding state. So at a higher concentration, the protein is not stabilized in the presence of same ionic liquid. So that means the protein stability is depending on the concentration dependent manner. So this is also similar results we observed. This is bromelain we have taken. So here also we observed same conclusion. Whereas in this ionic liquid, choline acetate, hydroxide, here somehow the protein is not stabilized because the nature of OH groups, it is making binding to the functional groups of the protein. So that's why here we observed protein is destabilized in this ionic liquid. So this is also another conclusions. We got same conclusion here also. So far we have seen these ionic liquids are stabilizing not only simple amino acids, but also in the globular proteins also. So what is the main chemistry behind this stabilization? So when you take the protein, when you put it in the aqueous ionic liquid, first the water molecules are forming hydration layer. Then these ionic liquids are trying to interact with the protein functional groups. But due to steric repulsion, these all ionic liquids are excluded from the water molecules at the protein surface. So you can see very clearly here, this is the protein structure. This is making hydration layer here. Then we are adding ionic liquid. So some of the water molecules are also coming this side, ionic liquid. So here you have ionic liquid with the water molecule hydration layer. This side you have protein with the water molecules hydration layer. Now two hydration layers are there. So they never interact, because hydration, water molecules never interact. So that's why here you are observing a steric repulsion. They're trying to interact, but due to steric repulsions, these ionic liquids are excluded from the water molecules at the protein surface. So that's why this ionic liquid is not interfering in the functional groups and keeping into the folding form. Then, whereas if you see the denaturants, for example, urea and guanidinium chloride salts, you can see here, when we add the urea molecules, you can see because of that nature, this is breaking the hydration layer. Then slowly it is interacting with a protein functional group and making preferential binding. You can see here, these all ionic liquids are interfering into the functional groups and making preferential binding. That's why in the presence of urea or any other denaturants, protein is getting unfolded state. Okay, so you can see here the difference when you have urea or some kinds of ionic liquids, they are making binding. These all molecules are going inside and making preferential binding between the urea molecules and the protein functional group. Whereas in the case of stabilization, here we are getting preferential exclusion and we are getting protein stabilization. So this is the main difference when protein is in folded state or in unfolded state. Okay, so far we have seen these all ionic liquids are stabilizing the protein structure. Then we can see contracting effect. What is contracting effect? You may take protein, then add ionic liquids, then these ionic liquids are stabilizing. Fine. We have seen just now the urea molecules are behaving like a destabilization. So here you can see this is stabilized, here destabilized, unfolded state. Okay, how to control this? So for this, if you combine these two solvents, this ionic liquid is controlling this action and keeping into the folding form. So here ionic liquid is controlling and keeping into the folding form. This we can say contracting effect. You can see very simple here. This is a denaturant and this is ionic liquid. This ionic liquid is controlling this action and keeping into the folding form. So now we can see how this ionic liquid is controlling. So when we add the ionic liquids, the transition temperatures are increasing with increasing the ionic liquid concentration. So that means this is control point. So up to here, the protein is stabilizing. That means it is folded state. Whereas in the case of urea, the transition temperatures are decreasing. So that means here you have unfolded state. When you combine these two solvents, you can see here the triangle points. These all points are under control. So that means these all are under the folding region. You can see the last point here, 1:4. We have taken 1 molar ionic liquid, 4 molar ionic, urea concentration. So this 1 molar ionic liquid is controlling and putting into the folding state region. So like this ionic liquid is controlling the urea action. Okay. So this is also same conclusion. Then refolding additive. So what is refolding? So here native structure, then we are making thermally denaturation to high temperature. Then when we add the ionic liquid, this ionic liquid is controlling this action and it is making again renaturation. Renaturation means it is folded state, then again unfolded, then again it is making refolding. So we can see how these ionic liquids are behaving, refolding. You can see here, this is native state, then unfolded, then we added ionic liquid. The epilicities, CD results almost matching. Okay, then we did NMR studies also. So you can see this is buffer without ionic liquid, this is ionic liquid, and this is refolding state. You can see the aromatic regions, NMR peaks are almost similar. So that means this is further evidence that this ionic liquid is controlling the, behaving the refolding additive against the thermal denaturation. So this is also same conclusion, and this is also same conclusion. So here you can see clearly this is folded state. In the presence of urea, it is unfolded. Then we add the ionic liquid, it is refolded. Okay. Then this is also chemically denatured protein refolding. So some of the results are highlighted in organic biomolecular chemistry on the cover page, which is behaving as a refolding additive against the chemically denatured protein. Then we have seen at low temperature also. You can see here this is high temperature. So here ionic liquid is controlled and it is making folded state. How about at low temperature? For that also we have studied. You can see here this is pure protein without ionic liquid. At low pH it is showing 5 degrees Celsius. When we add the ionic liquid, it is showing 2 degrees Celsius. So that means at 2 degrees Celsius, that means very low temperature also my protein is giving a folding state. Then this is similar results, and this is very interesting results. You can see here without ionic liquid we got relative activity 100%, 100. So whereas if you add the ionic liquid we got 2500. You may imagine 100 and here 2500 in the presence of this glutamic ionic liquid. So that means how it is enhanced the activity of this enzyme. So here also we observe same thing, other ionic liquids. And here we have different types of multiple denaturations. Here H2O2 and here guanidinium chloride and here time preservation also. In all cases also the protein is controlling and keeping into the folding state. So this is very surprising results. You can see at I almost finished it, sir. So here you can see without ionic liquid at low pH 62 degrees Celsius. That means it is denaturing. Whereas at same conditions, when we add the ionic liquid, the transition temperature is enhanced. So that means at low pH also my ionic liquid is giving protection. And this is also another results, and this is very interesting results. Yesterday we have seen organic talks. They're preparing drugs and many things to control the fibrillation and this amyloidogenesis, that is Parkinson or something diseases. So here also what we did, without this is protein at high temperature, it is completely got fibrillation. That means aggregated state. Beta structures are formed. When we add the ionic liquid, this is controlling and it is inhibiting this fibrillation and keeping into the folding form. That also very recently we have shown. These are the results. These are the results. So here also we are working biomass. In biomass also it is stabilizing the protein structure. So this is very interesting results. This is the, after juice we are preparing pulp, that is waste. From waste also we got some nanoparticles. That waste is giving protection to the lysozyme structure, and this is also some kind of biomass. So very recently one of my review article got a hot article in PCCP, very recently it got this one, and some of the results, very recently it is highlighted in SS Sustainable Chemistry and Engineering. This is the protein drug delivery results. It is got recently in the cover page, and these are my conclusions. You have seen already at high temperature, my ionic liquid is giving protection. And in the beginning, we have seen different kinds of stresses. So now you have to agree with me, please, because all my ionic liquid, whatever we have seen, the different kinds of stresses, all are controlled and keeping into the folding form. So this is my main conclusion, and this also we reviewed recently. These are all things in one journal. So here, up to here, whenever proteins are folding state in our body, there is no problem. When they unfolded or misfolded, then only we have different kinds of diseases. So for that, remember to laugh and don't forget to relax and enjoy and face challenges carefully. Then somehow you can control your proteins. So these are my collaborators. So these are my students. Because of their hard work only, I'm standing in front of you. So he is my first PhD student. Now he is associate professor in Japan. He is almost finished. So he completed in Taiwan postdoc position. Now he is working in Indian Oil Corporation, Panipat, and he is Avanish Kumar. He completed in MIT, Massachusetts Institute of Technology, first postdoc. Then now he is in Wipro University as a postdoctoral fellow. He is in South Korea. And these two girls are working in different colleges. So these are very recently, they completed their PhD. And recently she got Union Public Service Commission, geochemist. Now she is working in geo as a chemist. And these four are working in abroad only. At the moment, these 5 students are working in my research laboratory. Finally, I want to thank the financial support from DBT, SERB, and CSIR, University of Delhi for Institute of Eminence financial support, and also ISCA and RTM Nagpur University for their hospitality and their kind support. Thank you very much.
Thank you so much, sir. I request Professor K.K. Ghosh, sir, chairperson of the session, to present a memento to the speaker of the session, Professor P. Venkatesu, sir.
Thank you.
Any doubts?
No. Please, sir.
Insolvent.
Yes, sir.
And now
Yeah,
nowadays people are using amino acid based
Yes, sir. Recent.
comments about this amino.
Sir, because there in amino acid we have 2 less compatible, sir. Because already amino groups are there. Then again, amino group you are adding to the protein. These amino groups, and already it is there, some of the amino groups, they are getting more hydrophobic. When we are getting more hydrophobic, then somehow it is getting destabilization. We have done 2-3 works, but protein is not stabilized. I didn't show that results.
Thank you very much.
Sir.
There are large number of ionic liquids are known. And if you compare those ionic liquids with your ionic liquid, the activity difference is like 1-fold.
Yes, sir.
A 2-fold activity is not much different instead of publication point of view. If it is 10-fold, 20-fold, then it is useful in terms of.
Yes, sir. Yes, sir. Yes, you are 100% correct. Please. Definitely it will affect. It will affect. You may see my papers, we have done reverse and reverse also. We kept anion constant, different cations, one cation and different anions. We have done all the things. Due to lack of time, I didn't show all the results.
You are in Cambridge.
Yeah. Chemical review and also International Journal of Biological Macromolecule. There we have compared the 2 things, whatever you asked. Yeah, please.
Sorry, I'm asking very.
No, please.
Sir, your ionic solvents, they actually affect the enzymatic activity in intracellular conditions.
Yes, Vivo we didn't do. Vitro we have done so far. Vivo means I need some biological people help. I'm basically physical chemist. I can't do Vivo. So Vivo also papers are there. Literature is there.
We have used some enzyme alpha chymotrypsin and other.
Yes, sir. Yes, sir. That is Vitro only.
When you talk about in vivo, pH mentioned as 2,
Yes, sir.
and in vivo probably relatively
So time is important, sir.
needs
No
to
answer.
be 7 in it.
During tea time we will discuss you. Thank you very much for
Thank you, sir. Thank you, sir. Thank you.
आगे आइए। अच्छा, इधर केमिकल साइंस भी आ जाए ना।
My God.
same university, that is the University of Delhi, Professor Avasthi, Satish Kumar Avasthi. Basically, please join me in give hand to Venkateswar Nice and Professor Avasthi. And he is a organic chemist. And as you know that nowadays malaria research is very important. And he will discuss about this malaria research. And just for the student, I would like to tell that he is a very distinguished scientist. And he has got large number of awards from some international agencies and research fellowship awards like Tokyo Institute of Technology, UNICEF Fellowship Award, and of course, as you know, that is related with the medicinal chemistry, so large number of awards from Indian Council of Medical Research, International Department of Cellular and Molecular Medicine, even national awards, DVT Research Associates, Platinum Jubilee Lectures of the Indian Science Congress at Jalandhar, and a large number of PhD students awarded the PhD degree, 27, and H index is also very high, large number of citations, and he was a convener of this emerging trends in development of drugs and devices, and basically is a senior professor of the Delhi University, and he will speak on recent advances in malaria chemotherapy. So it is again, I am very really proud part of this program, so I welcome Professor Avasthi. Thank you, sir.
President of this chemical science, Dr. Ranjana Agrawal, who gave this opportunity to present our work. I also thanks to this university for wonderful hosting the large number of gatherings are over here. And I heard this Dr. Venkateswar talk. He is our colleague in the department, and he is very good speaker, and also he works very well. So it's always difficult to talk once he finishes. Anyway, I'll try my best to have something. But anyway, our talk is different from his talk because he is more or less physical chemist, and I am turned chemist to medicinal chemist. Anyway, what I'm going to present over here is recent advances in malaria chemotherapy. The reason why this is not my postdoc work, this is not my PhD work, because I trained as a peptide chemist, DNA chemist, and I turned into molecular biologist. When I was in US, I was working on the cancer biology. But if you find most of the people who are coming abroad, India from abroad, they are trying to use the same thing which they have done it over there. But I switched over my new field with the help of some student. I started my work on malaria, so design and synthesis of anti-malarial compounds. So I was basically organic chemist, so I was designing a small molecule and targeting to malaria parasite. Okay, my group is working on several aspects. That material science is nowadays very important, and if you go to around the conference, you will find 50% people are talking about nanoparticle, nanomaterial, and material science. So some of the students are also working. I am not discussing more. This is the material chemistry. That is also a small molecule synthesis. So this is using this material chemistry, we are making a small molecule for drug discovery. And this is application of nanoparticle and the use of covalent organic framework. And then design the small molecule, you need to test whether the molecules are working the biological system or not. So use the HSA binding, the human serum albumin, and I am going to talk on this one, the synthesis of a tetraoxane for the malaria drug discovery. Now question is, why malaria? Why not cancer? Why not COVID? Why not tuberculosis? Why not other drugs? The malaria is because if you look the statistics of the malaria patient, you will find the malaria is more predominant in poorest of the poorer countries, mostly like developing country as well as in sub-Saharan African. because malaria is not common in European countries, it's not common in America. So this is a kind of neglected disease. So WHO is putting a lot of money to develop a new drug for the malaria cure. Now, if you look this data, you will find from 2014 to 2018, the rate of the malaria patients were decreasing. In 2014, it was 217 million, and this is here 2018 is 228 million, and then suddenly it started increasing 19 and 20, 21, and then 22. So the malaria patients are increasing. This is the synonymic figure because sometimes the disease is up and sometimes disease is down because of a certain region. And if you look it around, you will find the Anopheles mosquito is a carrier for the malaria parasite because it has got the sucking pairs, and male mosquito is not harmful, and so it does not carry this parasite. Now, if you look at, there are 4 species. I am going little bit description also because some of the students are also sitting over here. So there are 4 species, and one is more common, it's a malariae. So this is Plasmodium falciparum, Novelski, Vivax, oval, and malariae. Now the red one is Plasmodium falciparum, that is more lethal, and if patient encounter with this strain, and if it is not treated in time, the patient dies. Now others are not very harmful. However, this strain is not common in India. It is not available in India. But India has got Plasmodium vivax, and if patient is treated, it can recover in a few days' time. Now, the most effective population in the malaria are young children, pregnant women, and travelers and migrants. And now, if you've got this malaria, you will find these are the symptoms, that is high fever, sweating, headache, nausea, and so on. Now, if patient is not treated in a time, suppose if it is encountered with the Plasmodium falciparum, and if it is not treated in time, then it will have a 3 severe effect in the human, that is cognitive impairment, and the respiratory dysfunction, and the renal failure. Renal failure is nowadays a very common disease once the malaria infection is there. Now this was discovered, the parasite was discovered by Charles Alphonse Levron and in 1880, and for this discovery he got a Nobel Prize in 1907. Now if you look the literature, because one can ask the question why not many drugs are coming very frequently. If you go around the lecture in Indian Science Congress Association, the 1,000 people are talking about drug discovery. They are showing this drug is showing antibacterial activity, this showing antifungal, tuberculosis, and cancer. But if they are coming so fast, then why there are no drug in the market? Because one drug came 15 to 20 years in the market. If you want to develop, that comes 15 to 20 year time of a span, and it requires billions dollars to get it into market. The reason is, suppose if you get it first stage in vitro, then it may fail in vivo. If it is passed to in vivo, then it may fail in toxicity. If it fails in toxicity, so that you have got clinical 1, 2, 3, and 4, and so on. So there is a very long process for the development of a drug against any disease. But if you look at this literature, you will find more than 70% antimicrobial drugs are based on the plant scaffold, are derived from the plant scaffold. It means the most of the drugs are still being isolated from the plant source, or once they are isolated, the activity is less, then they are further modified and get in the potential form. So the first drug which was isolated from the cinchona bark, it in 1820, that is the quinine, and now it is still effective against the malaria parasites. Also, now you see the time frame. This first drug was from the quinine, that is cinchona bark, and then this was a chloroquine that was chemically synthesized in 1934, and these 2 drugs are still effective against large number of malaria parasite strain. And then the primamycin and artemisinin and mefloquine. So these are the major drugs which are being used against the malaria parasite. Now this is the drug is known as a magic drug, and it cures all forms of malaria parasite, and that's why the WHO has recommended not to use as monotherapy but use as a bitherapy. It means you can have another drug. So formulations are known, and now you see if you look the literature, biologists and chemists, you will find this lady, the UU2, got Nobel Prize in 2015. She is not a medical doctor, she is not a scientist, but she was a simple person and got. And this is the lady, this is the person who got Nobel Prize for discovery of only one molecule, nothing else. Now this is the person, this is the lady, that is UU2, and the artemisinin is not, it was known for years and years, that is Artemisia annua, that is known as a sweet worm, was known in a Chinese as Puhangsu, and the decoction of this herb was being used by Chinese for more than 2000 years to treat the yellow fever, because yellow fever was very common in China and Asian countries, and the people are using for decoction. And after discovery, they found that it shows antifungal activity, antibacterial activity, antiviral, anti-tumor, anti-inflammatory, anti-lymphatic, anti-progenitor, and then, but it also shows anti-malaria. But it is the most effective against malaria parasite rather than the other, and this is that's why known as a magic drug. But it has got several problems. The shelf life is there, solubility is problem, and most difficult part is the synthesis of this molecule, because this molecule is still being isolated from the plant source. So then later it was modified and got the 3 compound, which is it is being used for the treatment of the malaria parasite. Now one can ask the question, last 2 weeks back, again the COVID is increasing, and the precautions were given by the government of India, and then the booster again started it. So if you look at literature, you will find the large number of vaccines are available. Now even COVID vaccines is available, though it is not very proven, and then the polio vaccine is available, cholera vaccine is available. But why there is no vaccine for the malaria parasite? Instead of only doctor prescribes a drug, and WHO had spent billions of dollars in getting this malaria vaccine. The reason is, if you look at the structure of this malaria parasite, is very complex. The life cycle is very complex. It is clearly divided into 2 parts. That one is a sexual life cycle, which is in the mosquito, and the other was is the asexual life cycle, that is in a human. So if you find any drug, if you find any molecule which is active against the mosquito, it may not work. It may not work in the man. And if you find any drug which is active against the man, a host, that may not work in the mosquito. And this is the reason till now there is no effective vaccine against the malaria parasite. Now, so based on this magic property of artemisinin, because it cures all forms of malaria parasite, so WHO has recommended not to use as a monotherapy but use in the combinations of other drugs, and these are the WHO recommended drugs. If you are using artemisinin ether, you can use this compound or this compound or this compound or these 2 compounds. So these formulations are available, and doctors recommend depending upon the severity of the malaria parasite in a patient. So now this is the simple mode of action. Now this is the heme. Everybody knows this is heme, that is the protein. Dr. Venkateshu was talking about the protein folding and misfolding. Now this protein is there, this is the blood is there, that is the heme is there, and now heme interact with the oxygen molecule of the artemisinin, and it breaks and it generates the free radical, and free radical is toxic to the malaria parasites, or malaria parasite did not survive because of the alkylation. And same is true in human, that all radicals are harmful for the human. So same thing is here. Malaria parasite cannot survive in presence of the free radical. Now the question is before the chem is, how can you synthesize this molecule? What are the simplest ways synthesis of this molecule? So if you look at the literature, you will find this artemisinin contains 3 oxygen atoms, and these oxygen atoms are essential. That is, the bond is essential for the activity. If you break this bond, then there is no activity. So that once it bond back, it generates the free radical, and free radical is toxic to the parasite. Now there are 2 possibilities. The scientists designed the first molecule, that is a triagen type, that it contains 3 oxygen, but this synthesis of this molecule was done after a great efforts, but this has got disadvantage in multi-step synthesis, low yield and less shelf life. Then the scientists think of making another type molecule, and that is known as a tetraoxane. And advantage with the tetraoxane is single step synthesis, moderate to good yield, high shelf life, and stable at room temperature. And there are 3 molecules are already in a clinical trial. And advantage with this type of molecule is it can reverse the drug resistance against the malaria parasite. Nowadays, the biggest problem in the drug discovery is the drug resistance. Most of the drugs are drug resistant against a particular disease. So if you find, if you see any antibiotic or any blood pressure medicine, the combination of two drugs. So if you there are 2 major groups in the worldwide who are working on this type of molecule. One is Paul Neal. He is in London. He is working mainly on the design and synthesis of different types of tetraoxane, and 2 or 3 molecules are already in a clinical trial. And the other one is Jarnej Iskra. That is, he is in Europe. He is working on this type of molecule. And then I decided to work on the tetraoxane, so I designed this type of molecule, and our activity is very close to the artemisinin. So there are 2 possibilities. You can design 2 types of molecule. Either you can have a tetraoxane with a symmetrical linkage, or you can have a tetraoxane with a dissymmetrical linkage, that is non-symmetric. So if you have got symmetrical type of molecule, then you can have a fewer possibility. You can have a less number of design. But if you have got non-symmetric, you can have a greater possibility to design a molecule with a large number of functional variability. Now, so you can, if you look at the literature, you will find there are mainly people use 2 types of catalysts for the synthesis. One is methyl rhenium, and the other one is rhenium. So if you look at the literature, you will find these are 2 catalysts for the synthesis of molecule. But suppose if you want to synthesize 1 molecule or 2 molecules, you can expend a large amount of money to buy a compound. But if you are working constantly on the same problem, you need to design 100 molecules, 500 molecules, 1000 molecules, you need a large amount of catalyst. But you cannot afford to invest 5 lakh, 10 lakh rupees only buying a catalyst and forget about the final product. So I was working on this molecule, then I thought this is not possible to work in without finding a new catalyst. So I looked, this methyl rhenium is a very expensive, 100 milligram costs 2,596. Then chemical nature is moisture sensitive and light sensitive and not easy to handle, and catalytic efficiency is 20 to 75%. Okay. And then other molecule which people uses very frequently, that is the rhenium oxide, is also expensive but less expensive than the first one. 2 gram costs 6,742. The crystalline and moisture sensitive, good efficiency 40 to 80%. Now here the basic difference between the Western countries and here, they work with the precise systematic way, because if you ask the student to weigh 5 milligram, okay, I will weigh 5 milligram, sir, 10 milligram, oh, no sir, it is okay, I will take a new one, they will throw into the sink. Without realizing it's very expensive. So I got this molecule, ammonium trioxide, after several round of screening, and it is very cheap. The 50 gram worth 1133 rupees. You can throw it, you can buy a new bottle without any problem, and the students will be also happy. And no moisture and no light sensitive, easy to handle, and good efficiency. That is, if you see the catalytic efficiency almost in the same range. So I started working on this molecule. So I got this similar result as in case of methyl oxide, rhenium oxide, methyl rhenium oxide, and then ammonium trioxide. And I got this one mole catalyst and hydrogen peroxide 2 equivalent, BF4 2 equivalent, temperature 25 times 60 minutes 47%. 2 minutes पहले बताना. ठीक है. So when you work on this medicinal chemistry, the failure is always there, and 98% failure, only 2% success. That's what I learned by working on this this type of problem. Publication is a different part. You can write anything, you can get it published, so you are happy. But if you want to go to little further, then it's always difficult. So I decided to work on this type of molecule, and then I decide 6 type of molecule. I'm going to discuss only one molecule here. That is, one is acyl type of compound. Then this is a alpha beta unsaturated type of compound. Then the triazine based compound, and the sulfonamide based compound. And then this is the hybrid compound. These are also hybrid compound. The reason is why you want to use hybrid compound. The hybrid compound always useful. If you look at nowadays antibiotic, you will find the combination of 2 drugs. One is A and one is B, and they are either in equal amount or in 60-40 or 70-30 depending upon the formulation. But both of the molecule will have a different effect and have a different role in the biological system. One may be excreting fast, other may be excreting slow in the patient. But if you have got the hybrid compound, when you are attaching covalent, it means will have a simultaneous effect, but it will be a synergetic effect on this. 2 minutes, okay. So this, I'm skipping this synthesis portion. So based on this molecule, we designed this type of compound, and if you see the artemisinin has got 5.97 nanomolar, and our compound shows 6.35 nanomolar, and that is very close to the artemisinin, and we got patent in 2016. We are not going to discuss NMR. When you are working the organic chemist, you need to characterize molecule. Now if you look this spectra of this compound, spectra of this compound, now you can see it is very difficult to characterize through NMR because of this aggregation, and even if you take the DMS, so the spectra of the structure will remain same. Then the only way is left, either you can characterize by crystal structure or you can characterize by C13 NMR. So I started characterizing all these molecules through C13 NMR and the crystal structure. Now you can see here this crystal structure confirms the formation of the right product. Now two types of compounds are sulfonamide type of and acyl type of compound. Now this so it shows that our design strategy works very well. And these are the biological data. That is the in vivo experiment. I am skipping the in vitro data. Now you can see here 1, 2, 3, 4, 5, 6, 7. These compounds are highly active against the malaria parasite in vivo, and they are comparable with the artemisinin. Just 1 minute I am sitting. Okay. Now if you, I am skipping all other details. Now if you see this compound 24, and now see the control. The control here is a chloroquine, and the compound 24 you can compare with this molecule, these 24 and control and others. You will find after 24 hours, this completely stop the malaria parasite growth, and this is also true comparing with these two figures. Okay, and then we designed different types of other compound, that is triazine based type of compound, and this patent was also filed in 2016. I got a patent was awarded very recently. Now you can see here, this has got 4.98 nanomolar, while artemisinin shows 5.32 nanomolar. So if any compound shows less than 100 nanomolar, this is always effective whether it is in vivo or in vitro. So we are working on this type of molecule, and progress is very satisfactory. These all compounds are less toxic, that is toxicity is less than 100 macromolar. And now these are some of the recent publications. They are, this is the malaria, recently got it published. The others are in the material science journal. Okay. I should also acknowledge Dr. Rajna Agrawal, sectional president, who invited me to deliver this talk. And I should also thanks to my alma mater, the University of Delhi, who's providing me bread and butter. Without bread and butter, nobody can survive. So I'm in the same boat. And then I got some from Indo-UK project, and then Nanomicrobe UK Limited, and Peptomer, that is the Indian company, and then UGC and DST. Of course, without DST, you cannot survive it nowadays. Okay. Now, just a minute. I personally say the other slides were not useful for me, maybe useful for you, but this slide is useful for me, and it should be also useful for you, because you may not be aware of this slide and you may not have heard of about this one. The first picture which I showed is, that was the, I'll show 1 minute, I'll take some 1 minute. Huh? For me, it is more important than the research. Yeah, this is our main building, that is where the administrative staff sits, that is the Vice Chancellor, Registrar, PBC, Dean Research. Other people are sitting other place. Huh? And this is historical importance, because the Viceroy Lodge was sitting over here. It is a residence of Viceroy in British period. And it has got the basement below this, where the Bhagat Singh was kept during the under trial, because before shifted to Karachi, he was kept over here, and the trial went, and after trial he shifted to the Karachi for the other punishment. So that's why for me it is more important, because most of the people they are not aware of where Bhagat Singh was kept and what happened after his trial. Yeah. So chemistry को आप slide सुनते हैं, but this is also equally important for the everyone. So Bhagat Singh was kept in this room. So his photo is there. Of course, the charpai cart has been changed, but this room is here. This is a very small room. There is no ventilation, and he was kept for some time during the under trial in a British period. So this is open twice in a year, that is 15th August and 26th January. So if you happen to be in Delhi, you please visit and enjoy it. Huh? These are some of my research scholars, because without this team you cannot get progress. So whatever I showed it here, the hard work of these students, some of the students have already left, they got some job, and some of them are over here still. They will leave it in 1 or 2 years. And one of my collaborators is also, I think he's presenting somewhere, Dr. Amit Bhattacharya. He was doing most of our biology work, and his spouse is sitting over there. Thank you very much.
Thank you so much, sir. I request Professor K.K. Ghosh, sir, chairperson of the session, to present a memento to the speaker of the session, Professor S.K. Awasthi, sir.
Yes.
And also invite our reporter, sir, Professor Chauhan, sir.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you, sir. Thank you.
So now it is, I think, tea time. So post lunch session, we have enjoyed very scintillating lecture, polymer regarding Professor Arvind Dikshit, sir, Venkateswaran ionic liquids, and most important, as you know, that malaria research and other things, and lastly,
Photo मिल गई
most
आपको?
important history, that is important, I think. So I am really grateful to all these distinguished scientists as well as the delegates for attending this post-lunch session, and enjoy the tea break. And if you have any problem, any question, you can discuss with Professor Avasti and Professor Tukadoji Maharaj. Thank you very much.
Thank you.
Thank you for giving me this opportunity. I am very grateful to Professor Maharaj. Thank you.
We'll start.
Kumar Dikshit sir with a floral bouquet. Arvind Kumar Dikshit sir to chair the session. Vice Chancellor of Dr. Bhimrao Ambedkar University, Agra. He was ex-member of UP Secondary Education Service Selection. He was chairman of NAC committee, worked as search committee member for selection of Vice Chancellor of State University member. He was sectional president of 103rd Indian Science Congress Association. He contributed in Ganga Manthan. He filed patents jointly with DMSRDE for scientific and social studies. He visited various countries. Now I request Mr. Ryan Pereira sir will highlight about fellowship opportunities in US.
Good evening, good afternoon, everybody. My name is Ryan Pereira. I'm with the Fulbright Commission in India. I'm going to talk very briefly about the Fulbright Fellowships because I want to start by thanking the chair for this opportunity to talk about the Fulbright Fellowships. So the Fulbright Fellowships was started by the US Senator J.W. Fulbright in 1946, and India has one of the largest Fulbright programs in the world. Over the last 70 years, we've given 21,000 fellowships. And the reason we are such a large program is because in 2008, the Indian government matched the US government in contribution towards the Fulbright program. So the Indian government is heavily invested in promoting the Fulbright program. So there are multiple types of Fulbright grants that we offer. We have master's, doctoral, postdoctoral, academic and professional excellence awards. So all these with the blue background are jointly funded by the Indian and the US government. And then we also have a few fellowships that are still funded exclusively by the US government, and the prominent one is the Hubert Humphreys Fellowship. So one caveat about the Master's Fellowship is that we require 3 years of work experience to apply for this, and there are 11 fields that are supported, and this grant gives up to $80,000 in financial aid. For the faculty members and the doctoral students, we have multiple fields that we support, and chemistry is very prominent amongst them. And I should mention that I'm a biochemist by training, so it's very nice to be in a room like this. So very briefly, for the doctoral, if a student has been registered for a PhD at an Indian institute, they can apply for the doctoral fellowship, and if selected, they can go to the US for 6 to 9 months, do advanced research in the US, and come back and complete their PhD from their Indian institute. For the postdoctoral, it's meant for people who have just recently completed their PhD within the last 4 years. And this is a very popular fellowship because you can go anywhere from 8 months to 2 years. And for the faculty, we have the Fulbright Nehru Academic and Professional Excellence Award. With this, you can go anywhere from 4 months to 9 months for the fellowship. We also have the Fulbright Column Fellowships. This is a more recent one. Again, we have doctoral, postdoctoral, and academic and professional. The focus of the Fulbright Column tends to be the broad range of climate studies. That's not for y'all. This is not for this audience. For the senior faculty here and those that are looking to build collaborations between your institution and the US universities, we have a program called the Fulbright Nehru International Education Administrator Seminar. If you apply and are selected for this, you go to the US for 2 weeks, and you interact with 8 to 10 US universities and start conversations about the collaborations that you can, that your university is looking for. The Hubert Humphreys is not for y'all. So what does the Fulbright Fellowship provide? You'll get the monthly stipend, you'll get the airfare, you'll get all the allowances that the US university might require. We'll also provide health insurance. So it's a fully funded fellowship. There's absolutely no expense from your part. What you all need to do is put in a very competitive application. So put in the effort to get a good project, try to understand how is the project valuable for India, how is it going to help the US, because those are the people who are funding it. Okay, don't just say, I'm a scientist, I'm doing really good science, and I don't care what the impact is. You won't get the funding. Okay? They're going to look at what's the merit of the project in terms of what is the impact that it's going to have. We're going to announce the fellowships, the next cycle, on February 2nd, and that's why some of the dates and all are not mentioned. And the application deadline will start from May 15th and go till July, August. So last year we have Fulbrighters from India in 27 states of the US. And the Fulbright fellowships are very prestigious. And part of the reason why they're prestigious is it's also very competitive. So last year we got 2,000 applications and we gave 138 nominees. So about 7% of all the people who applied got the fellowship. One of the characteristics, and I see a lot of women scientists here, is we try very hard to help the women, and so about half of all our awards are given to women scientists. Okay? So that's just our brief details. Again, usief.org. When we announce the awards, it will be on our website with very detailed instructions on how to fill. Everything about the application is done online. Okay? And there's an email address where you can contact us. So once again, thank you, President or Section President, for giving me this opportunity, and good luck to all of you all. Thank you.
Thank you so much, sir. I request Dr. Arvind Kumar Dikshit, sir, to present memento to Rayan Parira, sir. Thank you, sir.
Now I invite Senior Fellow, Professor Sankaram Padi, Arvamuth. Yeah, please come on there. As you are saying, Professor Sankaram Padi is retired in 2006, okay, from NEHU. He started his career from GAS College, Chittoor, Andhra Pradesh, in June 1965. Before he passed his MSc from Sri Venkateswara University, Tirupati. And you are the same fellow, yeah, same university. And he completed his PhD from IIT Kanpur, where I belong, in year 1975. He went to West Germany for postdoc. In year 1975, he got Max Planck's fellowship. As a scientist in National Chemical Laboratory, Pune, he worked from August 1979 for 2 years and joined faculty member Department of Chemistry, NEHU, in 1985 April. Okay, sir? He has been actively engaged in research in Department of Chemistry, NEHU, as a professor emeritus after retirement. Now I invite Professor Sankrampadi for invited talk. Time allotted is 15 minutes, sir.
Is it okay now? Is it? Audible? Audible? Yes. I thank the chairman for the introduction, kind introduction that is briefly given. And I thank the organizers, the sectional president and the RTMNU organizing committee for making it possible to come here and stand and make a presentation of my lecture. And I've been looking forward to this opportunity of getting invited to a Science Congress because I am planning to give an elementary introduction to what I have been doing since 1998 because it warrants it now. At all the time, I have been doing some calculations, making a presentation, and maybe I started with the International Society of Magnetic Resonance conference in Maryland Technical University. But all the time, it has been the result that I got and I worked at that time, and all the time it was an incremental research. Once I get one step, then only I know what I have to do the next to reach the final. But I knew there is an importance why this has to be pursued. We know what I want to do, but unless I make the first step and to some extent talk to the scientists, then I know what is the next step to do. So I call it an incremental research. Some people have this kind of a name for incremental research, it's step by step. But this work has been all the time so, and most of the time it has been a presentation of that time work and that result. Now I try to give a introduction from the elementary stage and what it can do, and not doing so much about what I had already presented. So this is an occasion for me to kind of cope up with what I should have done much earlier before I started working on this. And this is about the susceptibility and the shielding tensor in magnetic resonance. We know that once one has an information about the susceptibility, one can calculate the induced field and therefore the NMR shielding, NMR chemical shift. And this has been, that is, even if the shielding is at a proton which is not directly bonded to a carbon, somewhere in the molecule, still by knowing a susceptibility of that portion only, one can calculate the field and so on and so forth. There is an equation that is derived by McConnell. It is from the original quantum mechanical result. And so many people have applied it, it's all very well known. But this inception of this process of trying to, what I call the title page is up, the fragmenting the molecule and try to getting the shielding tensor. Shielding is, we usually use only the isotropic property. Actually the property is a tensor, and susceptibility, from there one can calculate induced field, is also a tensor. And in this case, I am not talking about fragmenting in the sense of degradation, but I am talking about considering atom level contributions, just as one talks about the ionization potential, electronegativity, electronaffinity, atom-based, and depending upon which molecule it is, a covalent bond, ionic bond, double bond, triple bond, and what does the electronegativity do in such context in chemistry? How does it explain the property of the functional group in the molecule and the total property of the total molecule? And the same kind of approach, if one does for the susceptibility tensor, then the advantage is this is applicable in solid state, which I actually worked it out because of an experiment. And secondly, it will be useful for the consideration of NMR of macrobiomolecules, biological molecules, and their secondary structure and tertiary structure and so on and so forth by NMR spectroscopy and compare it with the X-ray structure that one gets for such molecules. X-ray structures are usually in solid state, so one can't do it in fluids, so one can't get much near to the biological conditions. But people prefer these days, because of the possibility of the NMR, to do NMR three-dimensional structure determination and compare it with X-ray diffraction results. In such cases, already people have found out that the NMR three-dimensional structure is much more close and much more convenient for use in the case of liquid state and so on and so forth. It is useful for actual experimental interpretation of biological molecular structures, and this would be helpful in both these cases of solid state as well as, but it is not as simple to arrive at this, and as I told, it has been going on like a stepwise or incremental result, and now I am going to start with the beginning again as I started with the International Society of Magnetic Resonance Conference in 1998 and try to explain what it is all about. It's no question of degrading molecule, but consider only the atom level, if possible, of deep fragmenting in the molecule or fragmenting the molecule, and consider the atom-wise contribution or the functional contribution to the susceptibility tensor, and therefore you can use the functional group values to calculate the shielding even in the case when the neighboring molecule is not bonded part of it. That means in biological structures, particularly secondary tertiary structures, are usefully getting benefit from this kind of an information, that there is a part of the macromolecule coming from one helical part and another molecule from another part, and these two are but spatially closer, and therefore one can get a magnetic field induced. And the electronic information doesn't pass through so easily as much as the magnetic field, induced magnetic field. And therefore, I thought if one pursues it and finally gets a list of such things which is reproducing the original molecular value by summing, secondly, it is transferable from one molecule to other as well. Such a consistency, if it is there, like the, as I said, the ionization potential, the other properties of electron affinity and so on and so forth, how one can use it, one molecule to another molecule, and you can transfer it, get the information about all the molecules as far as the property is concerned. Similarly, if it is possible to do it for this, but this being a tensor property is not a simple number, it has units and dimensions and so on and so forth. One has to be very, very attentive to look into these details, and I'll try to go through it in simply in this 15 minutes, so there is not much time, so I'll quickly go through it. First, let us see this one. this already fragmented benzene. I started with the aromatic molecule because the benzene ring has the important contribution of the ring current on the neighboring molecules, and it is large. And similarly, one can try to work out with the benzene along with the ring current atom-wise contributions and try to go about doing it. First, calculate if this is possible to do such a fragmentation as I have been thinking about. Then it should be possible to calculate the intramolecular aromatic shift 7 ppm or so de-shielding. That value I must be able to get from these independent values and adding them. If I succeed, this is in a bonded structure because that proton is bonded to the molecule. So I break this molecule in the sense, not defragmenting, consider as part of so many. Just because I imaginarily fragment them doesn't mean that a physical property will get really distributed like this. So if I put a convenient borderline and say I want to have the property of this, the property of this, property of this, all of them are the same physical property, the units and dimension. Values are different because these are different functional groups and tensor and it is different orientations. Its principal axes are different. So if one can have such a kind of a situation and use these independent values, reproduce the intramolecular value, then intermolecular will not be so difficult, if this is possible. And secondly, for intermolecular cases, one can try to even do, as much as for this intramolecular, a quantum mechanical calculation. These days, the quantum mechanical methods are so much advanced and the computer facilities are advanced, memory, speed, and so on and so forth. One can put two molecules in structure editors which are not bounded and calculate the property. Therefore, for example, in this case, I can use this benzene molecule optimized, minimum energy configuration, put a hydrogen molecule nearby. That means I am adding a proton. Either I can have hydrogen atom or hydrogen molecule. Both can be verified. I have done both of them. So, the two molecules are not bonded. In that sense, I can place the hydrogen molecule at very, very far distances from the benzene molecule. There is no necessity that should be at such a particular distance. But the induced field from here will be different depending upon the distance. So, when I have a long distance, considering it as infinity, then the two shieldings of the molecules should be independently their own values, not influenced by either of the two, one by the other. As I bring them closer, even though there will not be any electronic bonding, still the induced field can be contributing at a distance of about 4 or 5 angstroms. Then the chemical shift that one observes for such a system, experimentally we can't do it. One can do quantum mechanically. So once you know the system, quantum mechanical calculation works, then one can put in a molecule closer to this without bonding, calculate the NMR spectrum and find out what is the shielding. Then move it out at a farther distance, what is the shift. If you take a difference, the difference should give us the value that this molecule contributes to it when it is at 5 angstroms. So this is the approach. I have some 19 slides. I am not going to present all these things, but I can only try to give you quickly the result for the intramolecular. These are the various distances for this. And this distance matters oriented theta and phi. This is for almost like a classroom lecture. Here it is. Now, in this you can find I have included 25 fragments of the benzene molecule. A simple benzene molecule, draw boundary lines, including a carbon atom and so on and so forth, CH bonds. These are all CH bonds, CC bonds, and there is one CH bond here, and for this proton, I try to calculate. Now, from this, there are various vectors, which I showed in the previous ones, and if I calculate whether this proton calculation will give me the experimental value or not. So I was able to get somewhat closer to the values for the true context where I include this proton calculation, where I don't include this proton calculation. I have two values, and how I calculate for this proton is something which is a equation and method which I have dabbled for 3 or 4 years and put it all in condensed matter physics. Because of this, it became possible to calculate the value for this bounded region. Otherwise, it won't be possible. So I am keeping it away. So that was a separately condensed matter physics. So I won't get into the details. But finally, I get these kind of a 7.4, 10.3 de-shielding values, isotropic values, which is closer to the solution in NMR spectrum. And I got many more of these non-bounded calculations. It's all there in the PPT points.
Thank you, sir. Now I request Dr. Arvind Kumar Dikshit, sir, to present a memento to the speaker of the session, Professor S. Aravamudan. Sir.
Thank you.
Thank you very much.
Thank you for inspiring speech in this age. Now I invite Professor Kallol Kumarji Ghosh, Head Department of Chemistry, Pandit Ravi Shankar Shukla, University, Raipur, Chhattisgarh. Please come on the dais. Professor Ghosh passed his BSc from the same university and attained 6th position in university ranking. In MSc, he got 3rd position and completed his PhD in 1986 from the Pandit Ravi Shankar Shukla University. Now, he is working in the same university as a teaching experience more than 30 years. 21 students got PhD under supervision of Professor Ghosh, and is 21. But mentioned here, yeah. And 6 students are working. It means, sir, your biodata is not updated. Sorry. Yes. Yeah. He's completed more than 1 dozen research projects funded by different government agencies like UGC, DST, CSIR, etc. Because I want to save the time in your biodata, now I invite for your talk.
Professor Arvind Dikshit, sir, and the distinguished scientist, like very senior Professor Shiv Satyaprakashji and my dear young friends. I deem it a really great pleasure and honor to be part of this 108 Indian Science Congress. I have no words to express my deep sense of gratitude to Professor Ranjan Agrawal and all the faculty members of particularly RTM Nagpur University, Professor Sudhakar Dhonge, my friends, Professor Karade, Professor Jugare, as well as all the faculty members for giving me this golden opportunity to discuss some of my very recent results to this all gathering. For the last 35 years, I have been working on the various important fields of physical chemistry. Particularly, we have developed some of the surfactant-mediated chemical reactions, and we have developed some supernucleophiles for the detoxification of some chemical warfare agents as well as some pesticides. But recently, some of our students are working on some protein-drug surfactant interactions as well as some drug and cyclodextrin interaction for antidepressant patients and other things. So I thought that in this Science Congress, I would like to discuss, because time is very short, initially they have given me only 10 minutes or 15 minutes, that studies on cyclodextrin inclusion complexation of some antipsychotic and antidepressant drugs. As you all know that depression is a very serious problem nowadays, and most of the patients are taking some of the antipsychotic drugs as well as some antidepressants without consultation of the doctors. And most of the patients are unresponsive to this type of these drugs, and there are so many side effects. And you know that after this coronavirus outbreak, that depression became a global problem. And deliberately, because I belong to Chhattisgarh, Pandit Ravi Shankar Shukla University, I have discussed with some psychiatrists that in our area, these two common drugs are taken by these local people, that is chloropromazine hydrochloride and promethazine hydrochlorides. And what happens, these drugs actually directly inhibit a very important, you all know that a neurotransmitter, acetylcholine, and that will affect the reuptake inhibitors of the serotonin. And there are so many side effects, some blood pressure problem, solubility problems. So therefore it is very essential to do some work with this thing, because I am a physical chemist, and it is a well-established fact that cyclodextrin is a very well-known pharmaceutical excipient, and that will of course affect the physicochemical properties of these drugs. Of course, that will also increase the solubility problem, that will also help to stabilize from the oxidation and sensitization process, photochemical cleavage. So our main objective is to use these drugs with the cyclodextrin. Now this is for the young students. Whenever we start any type of the work, we must know the national and international status of that work, whether work is going on or not. You will be happy to know that this worldwide, if you go to the literature, there are thousands of the papers. And this worldwide interest originates from scientists with the diverse specialties. And whether it is the organic chemist or the physical chemist, everybody is working on this thing. And I must mention the name of, just like your P. Venkateswar has done excellent work in the ionic liquid. Similarly, Professor Mahendranath Ray of the University of North Bengal, he has studied large number of this host gas complexes using all vitamins, all drugs, antibiotics, like on. Similarly, we have also published some of the good paper, but basically I was concentrated on the Alzheimer types of the drugs, the interaction of the Alzheimer drugs with this cyclodextrin and ionic liquids, and of course very hardcore NMR work for the actual complexation process. And some of my today's presentation is also based on some of my, but these are all, I have not published the main results of this thing. So this is the person actually, my research scholar, he has done this work. Now I can say the objective is very simple, that I have chosen these two most commonly used drugs in the Chhattisgarh and very well known complexation agent, that is the cyclodextrin. As you know, whenever we do such type of the work, so we must know the characterization of the things. And it's a very well known method, that means once we use the surface tension, conductance, UV visible studies, and in order to confirm the types of the complex, we have used that FTIR and DLS and fluorescence. And recently, we have already, an attempt have been made to use the NMR, and of course, you all know that nowadays, whether it is a physical chemistry or organic chemistry, DFT calculation, molecular mechanics is very important, and as well as some XRD disease. And lastly, because everybody wants some type of the activities, if time permits, I will discuss some of the antibacterial activities and cytotoxic activities of this type of the drugs. I will not discuss the specific objectives. Now, you know that any postgraduate students, post-graduation laboratories, we can prepare this type of the complex. We can prepare equimolar concentration of the cyclodextrin as well as this antidepressant drug. We mixed it and stir it for only for 30 minutes, and we evaporate it, and we just prepare, of course, purify with the help of this ethanol and other things. Once we prepared this inclusion complex, now the second problem is that we have to know the structure of this compound. So as you know that FTIR is the most important. Fortunately, all the instruments are available in our department. So we determine the FTIR spectra of alpha CD, beta CD, as well as both the complexes. And you know that if we compare the stretching and bending vibration of all these components, and there is a very close agreement between this type of the complexes. And I will not go into details about the stretching and bending vibration of the component, but it is confirmed that this complex is formed without any problem. Now, if you see the structure is very carefully, it is just like a surfactant type of the structure. So when we dissolve, both are water soluble compounds. When we monitor the surface tension of this pure drugs, of course, the surface tension is decreased. But when you increase the concentration of the beta cyclodextrin, so the surface tension gradually increases. That means this is the indication of the complexation, that pure drug is not available to change the surface tension. But a particular concentration, there is no change in the surface tension. Then again, same method we use for the conductometric titration. And you know that when there is a complexation process, because it is just like a torus-shaped molecule, so naturally the ionic conductance, ionic mobility is decreased, so conductance is decreased. And again, when you increase the concentration of beta cyclodextrins, again at particular concentration that is constant. Then when you compare the results, of course we have got this automatic tensiometer, and there may be some electrostatic interaction, van der Waals interaction, hydrophobic interaction, hydrogen bonding, release of conformational strains and other things. And when you compare the results, the host and guest, and if you see very carefully the concentration of this host and guest is almost similar, so that it indicates that it is one type of the inclusion complex. Now the question arises that how do we prove these things? So naturally you all know that the next step is the UV visible measurement. We monitor this absorbance spectrum of this compound with the increasing concentration of alpha cyclodextrin as well as the beta cyclodextrin, so 0 to 1 mole, and absorbance values increases. But what is important is that we have performed this experiment in 2 temperature in order to get the value of the binding constant, as well as you know that thermodynamic parameters is very important, whether it is thermodynamically feasible or not and other things. And it is a very common method for determination of this 1,1 complex. We plot a graph between this delta A, that is the absorbance difference of the pure compound and absorbance in the presence of the drugs, and the mole fraction, and we got the value of the R max, and it is almost like 0.5. So it is confirmed that there is a 1,1 complex. Again, further clarification is required. So you know that fluorescence is the most important method, but here we use some methylene blue as just a probe. Here, when you increase the concentration of alpha CD or beta CD, so that there is a quenching. You know, you can use the Stern-Volmer equation in order to get the binding constants, and Benzi-Hildebrand equation for the determination of binding constants at 2 temperatures. And when we compare this, it is just like your fluorescence in the absence of compound and fluorescence in the presence of. So the delta G value is of course negative, so it is spontaneous process, thermodynamically favorable process. Delta H is almost negative, it is an exothermic process. And when we compare the delta S before that and after that, so naturally when there is a complexation formation, so entropy decreases like that. Now lastly, when we confirm this binding constant by all these methods, and in beta CD case, it is 3.35 into 10 to the power 3 like that. And then we thought that we must know the actually size of, very recently we have purchased this Zeta sizer in our lab. We thought that these are all initial studies. We have not, so far we have not published all this information. So we have determined the size as well as the zeta potential. Unfortunately, we are getting some negative zeta potential. This is maybe due to some interaction and other things. And size also we determined. And of course, naturally, when there is aggregation, the size decreases. And zeta potential, we would like to again repeat these things, why we are getting such type of negatively charged of this zeta potential, and different types of concentration, different types of things. And we have got also XRD analysis. And you know that the angle of diffraction is a very important problem, and we can throw some light on the basis of this XRD analysis that because the XRD spectrum of alpha and beta CT is available everywhere, but we have seen three types of things. Some are, there is a disappearance of peaks, formation of the diffuse peak, appearance of the new peak. Of course, it is confirmed that there is a formation complex. And we thought that because we have done a lot of work in the NMR, but before coming over here, I asked my student just to take only two spectra. One is the beta cyclodextrin, another is the beta CT, because you know that in order to get complete information, we have to use the NOSI and COSI, correlation NMR spectroscopy. But one thing is confirmed that because if you know the structure of the cyclodextrin, so there are hydrophobic part and hydrophilic part in the exterior, and there are some hydrogen in interior part and the exterior part. So before that inclusion complex, when we monitor the chemical potential of this H3 and H5, and after the complexation process, it is again a, you can call it a qualitative study, very, very initial information. So there is a change in H3 and H5. This clearly indicates that yes, there is a formation of the inclusion complex. Then we thought that we must, this is the last part, we must apply some of the DFT process. This is a very big process because you know that it is not like a simple type of complexation. It based on many things for the young students, different types of the orientation, that which part is responsible for complexation process. So in this particular presentation, I have used only one type of system because that time was very short. I asked my students to just to apply the DFT analysis and with the help of some sister tool. And we monitor the HUMO and LUMO energy of all the species and all the complexation also. And finally, we determine the binding energy. If the binding energy less, we can throw light like, yes, this complexation is possible, but still it is under process. So we use first PDOs of the HOMO-LUMO plots of the complex 1. Complex 1 means alpha CD and my first drug. Complex 2 means beta CD and my first drug. Then complex 3 means alpha CD of the second drug, because the structure is very similar, but the nature of the behavior is entirely different. And then we apply this type of map density surface, and because it is a very long studies, the DFT analysis and all types of things. But ultimately, we got some fundamental results, because on the basis of these results, we can throw some light regarding this process, regarding the HOMO-LUMO energy and as well as the binding energy. But it is only for one direction. It may be temperature dependence. It may be, there are so many other factors that has to be calculated with the help of this. So this is only a preliminary study based on DFT. System can be fully relaxed for accurate results. And there is a possibility of preparation of many others configuration, and temperature dependence also there, and molecular dynamic simulation we have given. Now after doing all these things, I asked my students to do something work, whether this inclusion complexes show some cytotoxic activity or not. So it is also very common regular studies. I undertook this study with the help of some biotechnology department of our university, and I do not know much about the biology work, but once I understand these things, it's very simple that they prepare some agar-agar media and punctured this, in first 2 slides, they use this only drugs. And they use 2 types of G positive and E. coli negative. And they monitor the no inhibition zone and inhibition zone. Of course, it based on the concentration of that things. That is also very important in right test. But one thing is clear that the pure drugs, they inhibit this growth, but when we use this complex, so it is 100% confirmed that it is non-toxic antibacterial activity. So thank you very much. And so conclusion, you know that this is a 1-1 complex is formed, and I'm really grateful to my students. As you know that students are very important and they are doing the main work and other things, and ultimately this is our department. I'm really thankful to my department for all types of help, and of course thanks to the Indian Science and as the Nagpur University Chemistry Department for giving this 10 minutes or 15 minutes to present this work. Thank you very much. Thank you, sir.
Thank you so much, sir.
Thank you, sir. Thank you, sir.
I request Dr. Arvind Kumar Dikshit, sir, to present a memento to the speaker of the session, Dr.
Light
KK
on,
Ghosh.
light on.
KK Ghosh, sir.
Thank you.
Dr. Santanu Mukherjee. He is from the School of Agricultural Science, Swalni University of Biotechnology and Management Science, District Solan. You have 15 minutes time. Okay. Please be seated. As Dr. Mukherjee, he has completed 2 major research projects and 2 are sanctioned. I don't waste time in speaking biodata. Kindly come to the topic.
Good afternoon to all of you. So, first of all, I am thankful to Indian Science Congress for giving me such golden opportunity, and I am thankful to the organizers for inviting me. And now I will start my presentation. And again, I am happy that I can present my small work in front of August gatherings. So, honorable dignitaries are here. So, let's start with this. So, I will talk about a little bit different. It's a environmental chemistry. So, my topic itself is explanatory. You see the biochar and anthropogenic pyogenic biosorbent for contaminants. So, we all know about sustainable development goals. We all see these symbols around us in Indian Science Congress. So, we all know that there are 17 sustainable development goals, and my research area works with this 6 and 12. So, that's the clean water for, I am trying a small approach for the protection of the water contaminant or their sequestration, and also the waste management. So, we know all that our Honorable Prime Minister have emphasized on the work on waste management nowadays, and Professor Venkatesh also showed that how from biomass waste we can get nanoparticles. So, we all know this, that how the charred particles and the biomass carbon, they have a long series from slightly charred biomass to charred charcoal, shoot and biomass. Now, my topic is about biochar. What is biochar? Biochar is basically a biomass derived carbon. We can get it from local material, any waste material we can use it for the preparation of biochar. It's not a charcoal, it's a kind of biomass, any kind of biomass we can prepare from this. Like in Maharashtra, we can use the cotton husk, for example, for the preparation of the biochar. It's not a charcoal, it has the different application. Charcoal, we know we can prepare only from wood. So it's not a new technique. I am not telling that I am doing something out of the black box. So it was before in the Amazonian dark earth, and it was found by the previous Indians long ago. So, and it has been found that it can increase the soil carbon And nowadays we all are talking about sequestration of the soil carbon everywhere, so that there is a good soil health. Good soil health means good food health, and we can talk for food security. As I mentioned, the feedstocks of biomass can be different things. It can of any rice husk, cotton husk, even any waste material. We can prepare it through the pyrolysis process. We all know what is pyrolysis. All the doyens of chemical sciences are here. I am not from this, so I need not to explain the pyrolysis process. And in this pyrolysis process, we can get this solid residue that is known as biochar, and also we get little biofuels. And there are several uses. So we can use it for carbon sequestration, invasive plant management, and also it's a tool for solid waste management. There are different applications of biochar in soil, environment, and also for the sequestration of the organic and inorganic pollutants. So we know that different pyrolysis process, fast pyrolysis and slow pyrolysis. In fast pyrolysis, we have a we have a very limited temperature, and slow pyrolysis usually we apply mostly 300 to 800 degrees Celsius, and in fast we can go above 1000. There we have more yield of fuels, and in slow pyrolysis we have a more yield of char or the solid material. Now we all know that as biochar is a carbon black like material, charcoal like material. It can use for the different purposes, and it is a micro and macro porous area. It has a different pore surface area is very porous, so it can use for the sequestration of the different elements. Also, if we talk about the microbes can harbor it, and it can sequestrate the different contaminants. Now, and as I mentioned, it's a not new commodity. It can use for differently for the carbon sequestration, and we know in our northeastern part of India there is a slash and burn technique which is very much detrimental for the environment. Even in the Punjab, Haryana, we all know the issue of biomass burning, how detrimental it is, because it's a combustion technique. But it's not a combustion, it's a pyrolysis technique. So there is there is a very few chances, or there we cannot say that it's it is detrimental for the environment, because here we are not doing the open burning. And it has been recommended by Indian Council of Agriculture Research, Indian Institute of Soil Science, Bhopal, the recommended dose of biomass, and they has been found in the field trial. It is a very good technique. So we can say it's a carbon negative technique. We all know about carbon neutral, carbon positive, and carbon neutral technique. So we can say it's a carbon negative, because here there are more sequestration. Because we know the photosynthesis process, plant take carbon, and we are burning it, and we are putting it in the soil. So there is a storing of carbon. So it's a carbon negative. There is less emission, more sequestration. But we know the combustion, on the other hand, is a carbon positive technique, when there is a more emission. Similar like there is also a carbon neutral technique is also there. So as I mentioned, it's a part of the circular economy. And we know our government of India has last year also they have started the mission for circular economy, where there was a lot of issues and lot of talks about how we mention and how can we make waste to wealth. That is our aim. And we have the different growing, we can use it for the different plants, and for we also as a growing media for different purposes. Now, as I am from the Himalayan region, we all know there is issue of pine needles. There is a full of pine, deodar, all the coniferous trees. They are looking beautiful. Of course, they are the native there, but in Himachal, Uttarakhand, who are from there, they know the issue of forest fire. During particularly March to June, there is a pine needle falls, and then there is a lot of forest fire. Although it is not considered as a natural hazard, but we know that forest fire, this is a very catastrophic event. And they release lot of carbon dioxide to the atmosphere, and all wild animals and all other, even it is a loss for the environment also, because it has been found several soil nutrients are also lost through this process. And it has been found that in the 18 megatons of carbon has been emitted based on the analyzed satellite picture that Nepal emitted, and also the highest since 2016 when it is emitted 27 megatons of the carbon. So we know that this is a catastrophic event and we cannot stop it, and it is because of the pine needles. We all know they have phenolic compounds and they have flammable compound, therefore it catalyzes the forest fire. So therefore I use pine needles to prepare the biochar. And I live in the Himachal, and you know all that Himachal is one of the largest hub for the pharmaceutical industries. There are all pharmaceutical giants are there, starting from Sun Pharma, Dr. Reddy's lab, and for example, all other, even Cipla, all big pharma industries are there. So wherever there is industry, there is a pollution. And because, and then they are just, we all know this is a BBN area, and it is the one of the largest cluster of pharmaceutical industry, and they don't have the particularly common, we all know that all industry, they have the different treatment plant, and they do the primary, secondary, and tertiary treatment. But often we have found that they are, after primary treatment, they are just disposing their waste in the river water without giving the advanced or third treatment because of lack of facilities. Therefore, so this is area near the Punjab and Haryana border, and this is a pharmaceutical hub, and then there is a degradation of water quality because of their dumping of waste. And this is the Nalagarh area. You see the river quality. We have done a monitoring and we have taken the samples. And we all know the effects of the pollution of the pharmaceuticals or such emerging contaminants on the human and public health. And we have collected the samples, and our target compounds were ciprofloxacin, norfloxacin. These are the antibiotics, and also citalopram and cetirizine. My previous speakers has talked more about the antidepressant drug, so sir must be knowing citalopram is antidepressant drug. So, and also our target was to form cetirizine, that's anti-allergic medicine. And so we have collected the samples. So this was the all dumping waste near the industry, and we have checked all the basic water quality parameters, starting from pH, DO, TDS, these all basic parameters, and we have the ultra high purity liquid chromatography, where we have measured the PPCP, that is the pharmaceutical and personal care products, that comprises of antibiotics and these antidepressant drugs. And surprisingly, we have found norfloxacin and ciprofloxacin in a very high amount. You see, it's almost 1.5 to 277, and almost it's more than 100 microgram per liter. We know nowadays we are using often antibiotics, and the problem with antibiotics is these are the over-the-counter drugs. So therefore, what happened? It causes the antibiotic resistance. So we are taking, but it's not acting properly because of overactions. So this biochar and the reaction of the pollutants are well known. We know that there are the different reactions, starting from covalent bonding, electrostatic bonding, and biochars, they have the different functional groups, starting from carboxylic, phenolic, hydroxylic groups, and they interact with the different pharmaceuticals, with the organic and the inorganic groups. And also they have also the hydrogen bonding, electrostatic interaction, pi interactions. And as I mentioned that we can prepare it from the different process. And as I mentioned that it can be used for the remediation of the soil and water contaminants. We can use it as a filter material and in the constructed wetlands where we can replace it with the charcoal or activated carbon. And so some research we have done in lab and with the biochar for the removal of the arsenic. And we have found the good results because it was the low cost. We have collected it from the local materials, pine needles, and we have done this analysis in the ICP-OES for arsenic, and we are now working on the pharmaceutical waste. And as I mentioned that we have collected the samples and we have monitored the presence of antibiotics and antidepressant drugs there. And some literature study we have found biochar has the very good removal efficiency, and it has a very good time of removal. And the HP government is providing subsidy to people who are collecting the pine needles. They are giving per kg collection of the pine needles almost 2 to 3 rupees. And also we know the high cost of activated carbon, it's almost 60,000 to 80,000 per ton of powder. Whereas biochar cost, we can make 20,000 to 30,000 per ton. So here we see that how much saving we can do. Of course, the research is more needed for the large scale. From the pilot scale study, we cannot say anything. So here are some of the citations along with my paper and some of the other papers. And I am thankful to the Lancaster University UK who has giving me the fund, and also DST Serb from where I am getting the projects. And I want to make a small announcement. Our university is organizing a conference from June 21 to 23 on technological advances. So all the dignitaries present here, I welcome you all to our university and to see our beautiful campus and to join in the conference. Last but not the least, thank you for your presence, and I will be happy to have your questions, comments, and suggestions. Thank you.
Dr. Arvind Kumar Dikshit sir to present a memento to Dr. Shantanu Mukherjee.
Next speaker is Sandhya Lakshmanan. Please come on the dais. She is the university rank holder. He got gold medal in MSc. He's completed PhD with Inspire Fellow and postdoc work in Munich, Germany. At present, she is working in CSIR lab. Okay, please come on.
Thank you, sir. Thank you, sir, for your kind introduction. Good evening. Firstly, I would like to thank the organizers of India Science Congress, RTM University, and Professor Ranjana Agarwal for providing me an opportunity to present my work. Today, I will present my work on autooxidation of hydrocarbons, where the oxidation of simple hydrocarbons is studied to predict the complex reaction network for industrial purposes. And this work is based on high-level quantum mechanical study on oxygen-centered radicals and the development of a very complex kinetic network for oxidation reactions. First, autooxidation is a process of a spontaneous process of a compound in air. So, in the presence of oxygen, organic compounds can oxidize to hydroperoxides through chain reactions involving free radicals. This autooxidation process is central to both biological as well as chemical processes. For example, in cell membranes, the lipid autooxidation leads to lipid hydroperoxide. Here the autooxidation is not due to the molecular oxygen, but due to the antioxidants such as vitamin E and vitamin C. And this autooxidation is responsible for the oxidation of edible oils during processing. And the autooxidation leads to lipid hydroperoxide, and most of the secondary products formed from this lipid hydroperoxides are responsible for the off flavor during oxidation of edible oils. Most importantly, the autooxidation is a process of outstanding relevance in the industrial synthesis of aldehydes, ketones, and carboxylic acids through chain reactions. The efficiency of the overall oxidation reaction depends upon the efficiency of the respective initiation, propagation, and termination steps. So let us consider the example of the autooxidation of toluene. A cascade of intermediates starting from benzyl hydroperoxide to benzyl alcohol to benzaldehyde and benzoic acid is involved in the autooxidation process. The initial reaction of toluene with oxygen through hydrogen atom abstraction results in a benzyl radical and a hydroperoxyl radical, where the benzyl radical further reacts with molecular oxygen, forming a benzyl peroxy radical, This benzyl peroxy radical acts as a chain carrier in the rapid progressing reaction. Thus, in the chain process, this benzyl peroxy radical can again react with toluene, forming a benzyl hydroperoxide and benzyl radical. This reaction can be repeated several thousand times during propagation until there is no hydrogen source available or the chain is interrupted. But if the intermediates which can offer a weak CH or OH bonds, which were shown in the earlier slide, is available, the chain reaction continues. The benzyl hydroperoxide can again react with benzyl alcohol, forming a benzyl oxy radical, and again benzyl oxy radical on reaction with toluene forms benzyl alcohol, and the chain is now closed. So these additional reaction channels can also exist for the thermal decomposition of benzyl hydroperoxides, and one conceivable process is the hydrogen atom exchange between two molecules of benzyl hydroperoxide, which forms a hydroxybenzyl radical, which further dissociates into benzaldehyde and hydroxyl radical. The hydroxyl radical can again initiate the chain process and forming benzyl peroxy radical, and the chain is closed. The benzyl peroxy radical can undergo self-reaction forming closed shell molecules. Thus, the initial steps are a radical generating, and the cycles A, B and C are radical chain reactions, and the self reactions are radical removing reactions. Thus, on going from cycles A to C, it is well understood that the homolytic dissociation of benzyl hydroperoxide is the key step in generating radicals. But let's see the thermochemistry of these initial reactions. So the initial reaction of toluene with oxygen is a thermodynamically unfavorable reaction with a large endothermicity as shown here. So as we saw in the schemes before, the uni and bimolecular decay of benzyl hydroperoxide is responsible for the acceleration of hydroperoxides after a variable induction period. And now let's see the thermochemistry. The benzyl hydroperoxide dissociation is also not an efficient initiation process as reflected in the endothermic value. How about the self-reaction of benzyl hydroperoxide? Here, the self-reaction of benzyl hydroperoxide, where the hydroxyl group of one hydroperoxide attacks the hydroxyl group of other, forming two radicals with the concomitant water formation, is somewhat a better initiator, but still it is in the positive scale. So alternatively, the hydrogen atom, to our surprise, we found that the hydroxyl radical attack on the benzylic position of the second hydroperoxide, forming two radicals and two water molecules, is a thermodynamically more favorable reaction with a large exothermicity. So how well this bimolecular reaction competes with the purpose-built radical initiators? We all know that the dibenzyl hyponitrate and dibenzyl peroxide are considered as radical initiators. Dibenzyl hyponitrate dissociating into two benzyl oxy radicals is okay with 14 kJ per mole endothermicity. However, the dibenzyl peroxide is a thermodynamically unfavorable reaction with a large endothermicity as reflected in by the endothermicity of 140 kJ per mole. So, the reaction what we have studied, the self-reaction, is a better initiator, and this reaction is a prototype of the molecule-induced radical formation reaction, where two molecules react, two closed shell molecules react to give a radical pair or a biradical. So next, this can be treated as an alternative mode of initiation reaction in the absence of any purpose-built radical initiators. And here, this MIRF reactions depends upon the combinations of sigma and pi bonds involved. Accordingly, there are three classes of MIRF reactions. In the first class, where the addition of one pi bond to the other pi bond results in a 1,4 biradical. And in the class B, the addition of a sigma bond, the homolysis of sigma bond forms a radical as well as forms a radical pair. In the class C systems, addition of two sigma bonds results in a radical pair along with a new sigma bonded system. In practice, this new sigma bonded system is positioned itself between the radical pair such that the radical recombination is avoided. Here we explore the question of whether more than two sigma, class C type, and whether more than 3 sigma bonds are involved in the reaction. So as we saw in the thermochemistry before, the self-reaction of benzyl hydroperoxide forming a radical pair with a concomitant water formation is the favorable reaction. Here, the hydroxyl group of attack of one benzyl hydroperoxide on the benzylic position of the other, it activates the, it leads to a concerted overbond dissociation of the second benzyl hydroperoxide through activation of benzylic position. And as we know that all these requires the appropriate arrangement of the bonds and atoms in the transition state. So since overbond homolysis is the key step in generating these radicals, we look first into the potential energy surface of the overbond homolysis. Here we see that the reaction leads to a higher energy transition state and a radical pair minima. Here the radical pair minima is a singlet biradical, and the radical pair minima lies below the lies above the transition state because due to the flat potential energy surface and thermochemical corrections. And as we can see the natural orbitals, we see that the occupation number is almost equal to 1, showing that these are singlet biradicals. And then the self-reactions of benzyl hydroperoxide, as I discussed, there are two distinct pathways. One is the hydroxyl group of one hydroperoxide on the hydroxyl group of other. This reaction occurs through a reactant complex. Both the reactions occur through the same reactant complex and a high barrier transition state, forming a product complex which is not that much stable, leading to the formation of 3 products. The thermodynamically most favorable reaction where the benzylic CH bond is attacked, here the transition state, the energy barrier is around 20 kilojoule per mole, less than the other transition state, and it forms a very deep product complex with a high energy. And here we can see that the water molecule is placed between the radical pair, thereby the radical recombination is avoided. And so the same transition state can also lead to a more stable product complex with a higher energy, leading to closure products. We did not explore this pathway since our interest was on radical generation pathways. And now, whether these advantages of thermochemistry, driving force advantages, is also carried out to the reaction barriers. Let's see that. Let's discuss that in terms of the activation free energy and the activation enthalpy. We have the uni and bimolecular pathways. Here we also have the additional pathway of the reaction of hydroperoxide with toluene, forming the radical pair and water. As we can see here, on comparing the enthalpic energy barrier, the thermodynamically most favorable reaction has the low energy barrier when compared to the other reactions. However, on looking into the free energy, we see that at least at 298 Kelvin temperature, the entrophic penalty to bring the two benzyl hydroperoxide together is around 50 to 60 kilojoule per mole, as can be seen from the 3 reactions where the unimolecular reactions has not to pay. This penalty has not to pay by the unimolecular reaction. Thus, in practice, if we see that the uni and bimolecular reactions are the competition between uni and bimolecular reactions is close in terms of reaction barrier. But this reaction should have at least, but what we suppose is these reactions are largely dependent on temperature. Hence, from the study we conclude that the radical chain reactions are commonly initiated through the thermal or photochemical activation of purpose-built initiators, as we know. And where radicals come from in the absence of these initial strategies is much less obvious and is assumed to be derived from unknown impurities. So in the absence of purpose-built radical initiators, this molecule-induced radical formation can be considered as a well-defined alternative initiation modes. With this, I would like to thank Professor Ranjana Agarwal, Director, CSIR, NISPAR, and Professor Hendrik Zipse, my postdoc professor, University of Munich, Germany, and Professor K. Sendal Kumar, Bardiyar University, Coimbatore, my PhD guide, and the funding agencies like CSIR and CPCB. Thank you for your attention.
Oxidation doesn't proceed. Only catalyzed or photocatalysis or a photocatalyst. will be much simpler if trying out various kind of molecular combination in entire design. Because prototype can develop nano to certain phase or two. And just from the radiation, and then with the what molecular bonding structure, it's almost like auto. Even though it's called photocatalysis, once there is a catalysis, it happens almost like an auto. In fact, after meeting, this is happening in photography. These are all this is a biological process, and this is a simple chemical process. This auto oxidation and presence of conjugation there due to the radicals. First case is kind of photography.
Thank you, ma'am. I request Dr. Arvind Kumar Dikshit sir to present memento to Sandhya Lakshmanan ma'am.
Now I invite Professor Alka Agarwal from BHU for oral presentation. You have 7 minutes time. Okay, please.
This session and Professor Randina Agarwal giving me this opportunity to talk on my work. I have given only 8 minutes, so I have skipped most of the slides. I am just presenting my work which is going on in my lab. The synthesis of ciprofloxacin T3 bis 1,2,3 triazole conjugate by click chemistry as a potential antibacterial agents. My research interests are catalysis, synthesis of peptides, design and synthesis of acting antimicrobial agents, and modification of the existing drugs. Today I will discuss the modification of existing drugs. The drug development criteria should be easy, the synthesis should be easy, and the intermediate and the final product should be cheap. It is cost effective, and the eco-friendly synthetic approach, and negligible toxicity, and the other parameters. These are some compounds synthesized in my lab showing the very good antibacterial activity. These are the peptides which are showing. Ma'am, वो कहाँ से ले आते थे? Pointer कहाँ से? This is a peptide which is a benzothiazole and which is containing lysine and glycine. This is a benzothiazole and which is showing the 5 microgram per ml activity. And this is the another compound which is synthesized in my lab. This is the orthophenyldiamine derivatives, and this is a triazole nucleus. This is showing the similar antibacterial activity in comparison to the ciprofloxacin. And this is a chalcone derivative which is also synthesized in my lab. This is the triazole nucleus, and this is showing the similar antibacterial activity as to that's comparison to the standard drug ciprofloxacin. And this is another chalcone which is showing the activity. This is the isomers. This is the O group is here. The triazole is here, and here the chalcone is the upper moiety. And this is the benzothiazole moiety. This is the containing 2 bis chalcone, bis containing the bis triazole nucleus, and this is also showing the very good activity similar to the ciprofloxacin antibacterial drug. And this is the triazole and tetrazole containing moiety, and it is showing the 1.56 microgram per ml activity, which is very much active against ciprofloxacin standard drug. And this is the flavone derivative, which is we have catalyzed this moiety by preparing the flavone and containing the triazole nucleus, and we got the activity at 6.25 microgram per ml. This is similar to that of ciprofloxacin. And this is another chalcone is containing the another flavone containing the bis triazole nucleus, and then it is shows a similar activity 6.25. And this is also the triazole and tetrazole containing compound. It is showing the activity at 3.12 microgram per ml, and this paper is also published in European Journal of Medicinal Chemistry 2016. These are the another compound which I have prepared as ciprofloxacin derivatives, and this paper is published in 2022 in ACS Omega. These compounds are also showing very good activity in comparison to ciprofloxacin. We know that the ciprofloxacin has the bacterial resistance, so we have to need some changes in the ciprofloxacin drug. So we have used the click chemistry by inserting this triazole nucleus in this ciprofloxacin derivative and see the activity of our drugs. This is a commercially available ciprofloxacin hydrochloride drug, and which is free from the hydrochloride. By using the 5% aqueous sodium bicarbonate, we got the free ciprofloxacin, which are propagated with propyl bromide in sodium bicarbonate in DMF or state 48 or 100 degrees centigrade. We got the propagated product. And this byproduct undergo the C+2 cycloaddition or click chemistry with the azides in presence of copper sulfate, pentahydrate, sodium ascorbate, and DMF and water 4:1 and stay 20 to 30 hours room temperature. We got this compound, this containing the bis-triazole nucleus. And we have synthesized a more derivative, about the 20 derivatives of this synthesize for the structure activity relationship. This moiety is fragment for the under clinical trial antimicrobial agents. And this is the methylene chain for linkage. We are linking the ciprofloxacin moiety with the triazole nucleus. And then this is the effect of the halogen group we have substituted here, halo and chloro and methoxy. And the fragment, this is the ciprofloxacin antibacterial. After synthesis and purification, we characterize our compound by H1 NMR spectra and C13 NMR spectra. This is a propagated product. This B is showing here. This B is here. Is both B are coming here, and the A is coming here. This A, CS2 are coming here, and this is C are coming here. They are so. C are coming here and G are going downstream because this oxygen is attached with this group, and this. Other compounds are, protons are similar to that of compound. This J is coming here, is going the very downstream. We also characterize the compound by the C13 NMR, and this is the C13 NMR, our same compound, and this is the A and B are coming here. In A and B, the carbon atoms are coming here. This indicates that our compound has been synthesized. And this is the final product of triazole, bis-triazole containing ciprofloxacin derivatives. This compound is showing this B hydrogen is showing here, and this A hydrogen is showing here. It means that our triazole nucleus is prepared in our compound, and the other protons are similar to that structure. And this is the C13 NMR of this compound, and this also B and A are the carbon. These are showing carboxyl group, and this is the carbonyl group, They are coming here. This indicates that our compound has been synthesized. And this is another molecule which is containing into chlorofluorine, and this is also showing the B and A and here and here. This indicates that our compound has been, triazole nucleus has been synthesized and attached in our ciprofloxacin ring. And this is a C13 carbon NMR. This contains the chlorofluoro similar compound. This is A and B. These are showing. This is A and this is a B are showing A and B. This is another molecule containing the methoxy group, and this is also showing the C and B protons. C and B protons. This indicates that our triazole nucleus ring has been prepared in our group. And this is a A. This is a CS3. This A is coming CS3. This is coming here. And this is the carbon spectra of the same compound. What happened? Okay. And this is the D. This carbonyl carbon is coming here downstream, and C carbon is coming here. This is the carbonyl carbon, and the B carbon is coming here. This indicates that our compound has been synthesized. This is also another spectra of compound. This is also showing this. B and C protons are showing. B and C are protons are showing. B, this is B, and this is the C. This is the carbon spectra of the carbon derivatives, and this shows the C is coming carbonyl carbon, which is attached with the oxygen. It is coming here, and D is coming here, and the B and A are coming here. B and A, both B and A are coming here. This is CS2 and CS3. And we also characterized our compound by the mass spectrometry, and we got the mass spectra of this compound 4A. This is 718.2366, which is M plus H peak is content. We also characterize our compound by the X-ray crystallography, and we found the same structure of our compound. This is the triazole nucleus, and this is the chloro. This is the chloro group, and this is the oxygen, and this is bis triazole containing ciprofloxacin derivative. This is 4E is containing chlorofluoro. This is the spectra. This is the crystal data of the same compound. And after characterization, we go for the antibacterial activity. We have chosen a gram-positive and gram-negative bacterial stain and hemolysis of our compounds. This is the different groups which are used, dichloro, chloro, and bromoadeate. And our compounds are showing this is the 18.86 microgram per micromole. And our compounds showing the very good antibacterial activity 1.92, 1.94, and 2.08. And similarly, other compounds are also showing the very good activity. This is the propagated compound. 2 is the bis propagated compound, which is showing the very good activity against 1, 2, 3 bacterial stain or 4 gram-negative bacterial stain. And the hemolysis is also very less. It means our compounds are more active and their toxicity is very less. This is another compound which I have prepared, the series, and in this also, this is a compound containing 2,4-dichloro compound. This is 3.99 micromole, and this is the 18.86, and this is the dichloro 2,3-dichloro 3.99, and all the compounds are showing the very good antibacterial activity in comparison to the ciprofloxacin derivatives. These are all those other compounds which are also showing the very good activity. These compounds, this contains the methoxy group containing 8.86, 17.1, and this compound also showing the very good antibacterial activity again in comparison to the ciprofloxacin standard drug. This is a bar diagram of my compounds, and this is the ciprofloxacin. This is 18.86 micromole per ml, and these are our compounds 4B, 4D, 4E, 4H, 4J, 4K, 4L, 4M, and these are all the compounds. Best compounds are showing the antibacterial activity, very less concentration in comparison to ciprofloxacin. This is the S. audicis, and this is against E. faecalis, and this is S. epidermis, and this is against E. coli. In the nutshell, we have to conclude that a series of bis 1,2,3 triazole conjugate we have prepared in our lab with the different commercially available anilines and ciprofloxacin hydrochlorides, and the structure is of the compound is characterized by the H1 NMR C13 as well as mass spectral data, and we also confirm our structure of the compound by the X-ray studies, and in vitro we have done the activity of the compounds against S. audicis, S. epidermis, E. faecalis, E. coli, P. aeruginosa, E. hydrophila, S. typhimurium, S. paniculis, and the P. shingleroides. Among the derivative compound 2, 4H, 4J, and 4F display 2 to 10-fold more potential activity against most positive and gram-negative bacterial strains against comparison to the ciprofloxacin standard drug. In addition to this, I also showed antibacterial activity at MIC of 1.09 micromole against S. audicis, S. epidermis, E. coli, and which is 18 to 17-fold more potent than the ciprofloxacin. And this SAR study of the synthetic compound revealed that the compound bearing a strong electron withdrawing group at position 4 in benzene ring enhance the inhibitory activity. We conclude from the SAR study while electron releasing group decreases the antibacterial activity. Furthermore, the significance of present study was proved by result of hemotoxicity that our all compounds are very less toxic. And in future, the work will be focused on design and synthesis of multifunctional hybrids or drugs to establish meaningful structure-activity relationship and aim towards lowering of their effective concentration. This work is going on in my lab. These are the funding agencies where we are getting the funds. This is the BHU and this is UGC, and this is Institute of Science, Institute of Eminence. BHU is giving the funds for this, UKD, and the Department of Science and Technology. These are some selected papers which I published from our lab in 2022-21, and all the papers which are published in our lab. There are some papers which are published.
Thank you, Professor Agrawal.
These are the PhD students which are continuously working on these problems. And we also supervise the MD students of BMS, by Bachelor of Ayurvedic Medicine. These are my MD students which I have to supervise. And this is my prestigious Bharat Ratna, Pandit Manan Mohan Malviya University where I am working. I am very proud that I am working in this prestigious university, which is a Bharat Ratna, established this university. And this is the Ganga Aarti, famous Ganga Aarti of Banaras. Thank you very much for your attention.
Thank you, ma'am.
Please hold this. Sir, hold this. This one. This is CH bond, sir. Or this is CH and this is CH2. This B and this A. Sir, this is attached with the oxygen atom. That side is going to downstream. And this is not attached with the carbon atom of oxygen atom. That side is sir, this oxygen is there, no? This oxygen.
Okay. Thank you. Now, we have successfully came towards the end of this session. Now, I request Professor Khatti sir to accord vote of thanks.
Honorable dignitaries, invited speakers, oral speakers, and all my colleagues, those who are sitting here, students, teachers. I'm here for presenting formal vote of thanks. I would like to thank, first of all the chairpersons who have chaired the session and cooperated to Indian Science Congress 108th session, which is conducted by RTMNU. I'm also very much thankful to all the invited speakers, those who have given very good presentation, very good insight to different topics in this today's session of the 5th January. I would like to thank the speakers of the oral presentation and all the students and my colleagues, those who are listening to all that. It is from my bottom of heart. I would like to thank all of you for this kind cooperation to RTMN. Thank you very much.